Oh, good afternoon. This case history is intended to present an example of how a risk-informed design process, our RID process, was applied to optimize a design concept for a spillway enlargement project at the Tule River Dam site. And specifically, we'll focus on the geotechnical site characterization and geotechnical failure modes that the RID process was associated with in terms of evaluating the design features and components for this enlargement. The Tule River Dam is located east of Porterville, California, in the southern San Joaquin Valley and north of Bakersfield, and it's positioned at the lower elevations of the Sierra Nevada foothills on the east side of the San Joaquin Valley. On the right side is an aerial image and some photos and a cross section of the embankment, kind of showing the typical max section for the dam and the layout of the project. For the most part, we'll be focused on the emergency spillway located off the right abutment. One thing to note is on some drawings and some references, this dam has also previously been called Richard L. Schaefer Dam or Success Dam. The name has changed over time periodically, and some of those names still are on some of the reference figures and documents. Okay, so to start things off, we're going to go back in time a little bit, 2015, for the baseline risk assessment. The first risk assessment performed for Tule Dam, and a whole slew of failure modes were identified. A lot of them related to the dam performance, seismic issues, gate issues, and that sort of thing. But the primary risk-driving failure modes were identified as overtopping of the main dam and overtopping of a dike that's located further up in the reservoir. The decision makers at the Army Corps, when they reviewed the project, reviewed the risk assessment, made recommendations that the teams look at performing a dam safety modification study. So evaluate the structural or other types of alternatives that we could implement to reduce the risk of overtopping at the project. The design teams came up with a concept of enlarging the spillway, so increasing the capacity of the existing spillway. And this was broken into two phases. Phase one would be widen the spillway channel invert by about 120 feet or so. That'd be done by pushing the right spillway cut further to the north and then relocating one of the access roads that goes around it. And then phase two would involve the raise of the spillway crest by about 10 feet to increase reservoir capacity. And this would be done with an arched OG weir structure with apron and training walls. So I should note that phase one was a little bit too far advanced in the design and the process and the funding mechanics to implement RID on that phase of the project. So we would focus on phase two for the most part. Okay, so we have a overall layout of the existing spillway configuration. So the spillway itself is located in a deep cut about 750 feet to the northwest of the right abutment of the embankment dam. The spillway itself is unlined, and the invert generally composed of variably fractured, variably weathered granitic intrusive rocks and some metasedimentary rocks with some intrusive veins and dikes and that sort of thing, typical of the foothills in the Sierras. The cut is about 120 to 140 feet deep across, perpendicular to the right abutment ridge line. And the invert itself is about 250 foot wide. So that would have to be increased for the mod study repair. The sill, the current layout has a concrete control sill, and it's about 39 feet, 40 feet below the crest of the dam, and it was constructed into about a 6 foot deep trench, and it extends up the abutment side slopes. We'll see a picture of that in a minute. Approach channel is about 500 foot long, and the discharge channel, the downstream discharge channels, on the order of 700 feet long, and it's all relatively flat. It's about a 1% grade. And then downstream, the channel re-enters the existing drainage system that's downstream of the right abutment ridgeline. So here are some general photos and some layout pictures of the construction of the control sill. So on the upper right, we're looking downstream, of course, and we see the right abutment sill and the left abutment sill kind of be embedded in and come up the rock mass. I don't know, 10 to 15 feet or so. And then in the center, you see the construction photo where we have the 200-foot long, 3-foot wide control sill that's socketed into 6 feet into rock. The entire spillway channel was excavated using blasting methods. All right, and so here we are looking at a series of photos of the left abutment in 1959 during construction, as the operators were getting down toward this existing invert elevation. A wedge-shaped slab of rock failed out of the left abutment cut. The wedge was formed by adversely oriented joint sets and some tension cracks that were forming the rock mass on the left abutment. And one of the primary things to note is that the sliding plane, the basal sliding plane controlling this wedge slab, has an out of slope orientation. So that means it's dipping toward the spillway, and it represents a potential, sliding surface, sliding plane for rock wedges and rock slopes. So the other thing to note is that this feature is seen in other construction photos and in the field. So we have this out of slope dipping joint set that is potentially a little bit adverse. However, over the duration of this project, since this 59 small slab failure, there's really only been small rock blocks raveling off the slope on both abutments. There has not been reactivation of this failure or any other large scale or similar large slab failures on either abutment. All right, so now here we're looking downstream in the upper right photo of the current day configuration of the Tule River spillway cut. We've got the right abutment slope that's cut at about 1:1. We see the existing sill coming up the abutments a bit. Right at the left abutment, the slope was steepened to about 1/2 to 1. The overall slope kind of upstream of the sill and downstream of the sill is about 1:1, but you can see the area in the middle. It's kind of highlighted by the yellow dash line where that rock slab, that wedge failure occurred. They regraded or flattened that slope a little bit to about 1.3 to 1. That's shown in plan view down in the lower left image, where the kinematically controlled slab is shown, and then the regraded or the flatter area highlighted in the pink. The only spillway flows that have ever occurred at the Tule River project were in 1966, and we had a peak discharge of about 8,300 CFS come through the spillway weir, and it's shown on the hydrograph below. You can see it's a very sharp peak, and it dropped off fairly quickly. The peak only was flowing for a handful of hours. However, it flowed, the overall duration of the spill was on the order of 120 hours that passed over the sill. Downstream of the invert, downstream of the construction spillway floor, where it re-enters the natural drainage channel, there was erosion that was observed. So the erosion occurred where all that water concentrated and increased its energy and went back into the natural erosion channel. And so there was some previous erosion that did occur with this 1966 spill. One thing to note too are all the surface drainage gullies and drainage reentrance or swales on the downstream side of the right abutment ridge crest and on the upstream side actually. But all those are coalescing and getting into the main reentrant channel downstream of the spillway, and then getting back into the Tule River spillway or river downstream. We'll discuss this a little bit. All right, this image shows the general topography in the mountainous area off the right abutment and up the hill slopes above the spillway cut. And what we see are the ridge line, the right abutment ridge line, which comes down along the, the high points along that feature, and separate drainage basins or smaller scale drainage areas. The next thing we see are all the drainage features, right? We have the contours which dive up into each of those little drainage channel alignments, and we see all the drainage is flowing into a collection drainage up above the spillway, and then downstream right at the spillway where it makes that turn, that's where the natural drainage occurs to get back into the Tule River. Okay, so now we're able to look at the right abutment of the dam and the alignment of the spillway on a pre-construction aerial photo. And we can see the spillway cut I've annotated on there, and you can kind of see the drainage reentrance. So the first thing notice, all these drainage reentrants, we map all of them and tie them into the higher order streams and drainages. And we see that the drainage reentrance turns like almost 90 degrees at the base of that, at the downstream end of the spillway, the future spillway. And we also see our ridge line, the ridge crest, which comes across the center part of the spillway, which was cut, again, about 120 to 140 feet into that ridge rock mass to cut through the high ground there. So the one thing to note when looking at the geomorphology of an area is that the drainages and the geomorphic expression tend to exploit geologic defects or weak zones. So this can be contacts, fracturing, shears faults, differing material strengths, weathering zones, alteration zones, contacts between bedding, contacts between intrusives. So anywhere there's potential for weakness and area where water can exploit it, that typically represents where the waters will start to erode and start to downcut and create drainages and create these surfaces. So a lot of times the drainages reflect the underlying geologic structure. And the thing that we note from all of the pre-dam aerial photos and maps is that there is not a significant lineation or drainage feature or trend, tonal trend or erosion trend that crosses perpendicularly the ridge crest at the location of the spillway. So this suggests that possibly we don't necessarily have a significant geologic defect or structure or feature that crosses parallel to the spillway alignment. The regional geology in the area consists of older metasedimentary rocks and metavolcanic rocks that have been subsequently intruded by younger granite domes, granite intrusions that have come up into those host rocks, those overlying host rocks. And they come with a lot of hydrothermal alteration and dikes and veins that extrude out into the overlying rock mass or discontinuity features. This is very common of the Sierra Nevada batholiths, especially in the eastern part of the Sierra Nevada foothills. All right, so using the spillway floor and spillway sill cut mapping, control sill trench floor mapping, aerial photo and delineation of lineaments and features that can be observed in the cut slopes, delineation of weathered versus unweathered zones, and the field mapping effort are all compiled to understand the geologic conditions, the fracturing, the location of shears, the areas of contacts that we may need to look for. For the most part, the mass of the spillway is excavated through what would be characterized as fairly competent granitic or quartz diorite type bedrock, but there's clearly zones or pockets of highly weathered rock or more intensely fractured or broken up rock zones. These zones need to be more clearly delineated, and that's what we do further on in the field studies. Based on the field observations and field mapping, we were able to identify areas where there was more intense weathering. And one thing that does jump out is that there seems to be a weathering rind across the top of the granitic and diorite intrusive rocks on both abutments. And then there's areas or pockets, as I mentioned before, of more highly to moderately weathered and highly fractured rock. So the key for spillway erosion is to try to identify or map out spatially, vertically and horizontally, where these areas of more erosion susceptible rock masses may or may not exist, and try to extrapolate those in the direction of the erosion and with depth, and to understand those areas a little bit better. So that's what this map is compiling, all of the observations and all of the field information that we are able to compile from the drilling and the field mapping and other efforts. We were fortunate enough that during original construction there was geomechanical mapping of the sill base, the floor, and also a cross-section compiled looking downstream. So that's what's shown here. On the top we're looking at the sill floor and plan view, and then down below we're looking at the sill slope, right, like a cross-section along that sill alignment. And the main takeaways from this are that there certainly are shears and faults. For the most part, it's granitic and diorite in the foundation, but on the left abutment, we can see that there's some more highly fractured zones with a shear that dips back toward the left abutment, and there's also a contact in that area that's related to maybe a quartzite host rock that's been engulfed or encapsulated by the intrusion. So there's probably contacts, there's probably alteration, and there may be more intense fracturing on that left side. And that correlates with some of the observations we saw. So during some of the field exploration and mapping efforts, the teams were able to identify and delineate these areas of good versus bad or poor rock masses. And for the most part, across almost a majority of the sill invert foundation, we see that we have moderately to unweathered and moderately fractured granitic rock that is of high rock mass quality. It has well over 10,000 psi for the unconfined compressive strength. The joints are somewhat blocky and discontinuous, and it makes up a very highly resistant rock mass for perhaps 90% or more of the entire spillway foundation. But similar to what we saw in that last section, on the left side of the spillway invert toward the base of the slope, there was a zone that was identified that looked to be slightly more weathered. It was highly to moderately weathered and more highly fractured, and this correlated with lower unconfined compressive strengths of less than about 5,000 psi. And this is the material that also is exposed in the erosion channel at the downstream natural drainage reentrant. And we can see in these lower photos where the erosion that occurred in 1966 was able to exploit that highly weathered to moderately weathered granitic material that's near the surface, that's been exposed, that's near the channel perimeter. So the curious question is, does this material extend all the way up to the sill in a continuous, wide, and deep mass, or is it confined to weathering in the near surface associated with the channel and the rock slope in the natural topography that's downstream of the spillway invert? All right, so now we have a little bit of a concept of the geologic conditions in the abutments and abutment cuts and the spillway invert. So let's talk a little bit about the design. Phase 1, as I mentioned before, the project was broken into phases. Phase 1 would involve pushing the right cut slope about 120 feet to the north, and then relocating the access road above the planned new weir crest elevation. Phase 2 would involve construction of a new concrete arch spillway weir about 10 feet above the current sill elevation. We would flatten potentially flatten the left spillway cut to improve stability. And then we'd add anchored training walls on both sides of the spillway. And then the design also involved putting 2 drilled key walls, so like a erosion resistant cutoff wall at the heel of the arched weir and at the toe of the apron. All right, so this is the preliminary phase 2 weir structure design, and this was what we had going into the RID evaluation, the risk informed design evaluation. We have the new arched concrete weir to transfer loads out into the abutments. Both abutments would be protected with a bit of an upstream and downstream concrete training walls. And then will extend the new apron in a downstream direction. And on the right, we see the cross section. So we see that we have almost 9 feet of excavation into the rock, into the existing spillway invert. And then we have the 2 key walls, whoops, that should say downstream, but downstream key wall on the right and the upstream key wall on the left. And these were intended to extend at 20 to 30 feet and be constructed with large diameter columns, drilled columns through the granitic rock in the foundation. Okay, so real quick for reference, throughout this process, the risk cadre and the district got back together in 2018, and they did not look specifically at the design details of the spillway. What they looked at more in general was, did the new spillway design adequately pass flows so that we would reduce the risk of PMFs related to the overtopping? And the findings were that yes, the new spillway design, the enlarged capacity of the spillway, would reduce the potential for overtopping and improve our risk related to those failure modes at this project. So risk-informed design at the Army Corps is dictated in Engineering Construction Bulletin 2019-15, which requires risk-informed design as part of project delivery. So this is to help ensure the designs meet USACE tolerable risk guidelines and develop a basis for design for uncertain engineering conditions or decisions. So for our case, we wanted to look at potential for scour, loading on the weirs, the abutments and cut slope stability issues, structural stability, sliding stability, and put this into a risk framework, which had not been done in that amount of detail in the previous risk assessments. The other thing is this helps us identify vulnerabilities and susceptibilities to the design, because there's always a possibility that a design element in a project might actually cause an increase in the downstream risks. So we got to put that into context. The other thing that the RID does is help us optimize the design and focus on the more susceptible elements of the project rather than just take a template off the shelf and use as traditional concepts in that design. And this also helps improve our communication of major design decisions. And the RID is scaled to fit the schedule and scope of the project. So it's a little bit different than our SQRAs or QRAs, which have a very robust amount of work and expectation. The RIDs can be scaled to fit the project more appropriately. Okay, so I think this is sort of a repeat slide, but the point here is that the phase 1 involved cut slope construction, pushing the cut slope on the right side 120 foot to the northwest, and that was not part of the RID evaluation. It had been too far along, and we weren't able to include it in the RID evaluation. But what was included was 35% design for construction of the new arched OG weir with the apron training walls and the upstream downstream key walls, and then regrading of the left abutment slope. So that's what we were mostly focusing on in this effort. Okay, so we're going to go over a little bit of the field data and the information that was collected that we had to work with respect to performing the geotechnical risk assessments for the new weir structure. A lot of this information was collected between 2018 and 2019. It included field mapping, geotechnical drilling, sampling, and lab testing, in-hole or down-hole televiewer logging, and then superficial geophysical refraction surveys and some other information. So we'll run through all that as fast as is practical. All right, so the SPK district, Sacramento district, had developed these processes, I believe, for Isabella and possibly other projects where they made criteria and defined their various weathering degrees for granitic type foundation rock, and it ranged from, decomposed granite to highly weathered, moderately weathered, slightly weathered, and unweathered. And they have a lot of criteria, a lot of evidence, or a lot of cross-referenced information that can be used to map or delineate or log the granitic rock according to these weathering grades. There's also other weathering grade criteria and tables that are useful to use. Another way to do this would be to use, for example, a GSI type mapping of the rock mass, where that includes both weathering grade but also fracture intensity. But SPK also was able to bring in the degree of fracturing into their mapping. So here are the examples of the mapping that was performed at the Tule Spillway. It was broken into the left abutment, invert, and right abutment. And what we see is they were able to delineate the type of weathering that the rock itself was experiencing, and then how much fracturing went along. So they used this symbology to identify areas of highly weathered and highly fractured versus moderately weathered and moderately fractured zones. And that kind of helps put it in perspective of where the poor rock mass is versus the more competent, more resistant type rock mass. All right, so here's the mapping of the invert of the spillway, where they're using the same criteria we're referencing above. But the thing to note for the invert map is that there's this moderately weathered, highly fractured, and then highly fractured or highly weathered downstream area along the left side of the spillway, kind of near the base of that cut slope. And maybe that correlates to what we were seeing on the left side of the spillway mapping, the spillway trench mapping. So what is it that we're worried about here now is that if we have erosion that concentrates in the downstream gully, is it possible that it exploits a buried or unknown, highly weathered, highly fractured zone along that left side of the spillway, and it can erode head cut to the apron and fail our structure? So that was a concern for the team and for the designers moving forward. And then here again is the right cut geomechanical type field mapping, where they've identified all these areas, and we can see that for the most part the weathering does tend to follow the topography. So there's a weathering rind on both abutments. It's pretty clearly composed of almost decomposed granitic rock or highly weathered rock that follows, for the most part, follows the contours. And when you get down into the heart of that ridge, or at the deepest part of the cuts, we're in less weathered, less fractured, or more competent rock masses. But there's occasionally pockets or areas or zones along discontinuities that do become highly fractured and highly weathered. So we have to be able to understand what the spatial extent is and distribution is of those highly weathered or challenging zones, and figure out if those exist in the area of the spillway flow. All right, the typical geotechnical subsurface data collected, compiled, and synthesized throughout the project utilized all of the rock quality parameters that were measured out in the field and in the mapping. So RQD, RMR, rock mass rating, the weathering, the fracture intensity. And what we see when we compile all this information is that for the most part, all these parameters improve with depth, particularly below about 20 to 40 feet or so. So the rock quality improves, the strength improves, the weathering reduces, and the fracture intensity becomes less tightly spaced. So we have overall in almost all the drill holes and almost all of the data we've got is that this improving rock mass quality with increasing depth. And most of the spillway invert is well over this 30 to 40 foot below the original ground surface, if we remember. So it's probably mostly on the order of 100, 120 to 140 foot deep through the most, critical part of the spillway invert. Just a quick statistical graphic showing the relative unconfined compressive strength of the different weathering grades that were identified in the granitic rock. And for the most part, the average of all the rock mass that was better than moderately weathered had an average PSI of about 20,000 pounds per square inch. And so it's pretty, even the moderately weathered granitic rock is got really high unconfined compressive strengths. Now we also have to realize that it's the degree of fracturing and fracture orientations and that sort of thing that may control erosion, but that's a good indicator of pretty competent, strong materials, at least the intact materials. And then the highly weathered material is very weak. It's in that geomechanical zone of less than about 3,000 psi, where it is weathered and can be eroded and plucked and particles just pulled out of that type of material. All right, here's a layout of all the geophysical lines that were run, the refraction lines, and we have a number of them that cross the spillway invert, run upstream to downstream, and cross from left to right across the spillway base. So we'll look at a few of those in more detail. An interesting sidebar related to rock erosion is that the SPK district did a ripability study at Isabella Dam, which is actually located pretty close to Tule River Dam and within probably similar granitic intrusive type masses. And they did this ripability study in the granite rock there, and they found that in general, when they had seismic compression wave velocities of greater than about 5,000 foot per second, that material became virtually unrippable. They had very difficult time ripping through it with the shanks on a dozer. And so they used that criteria as a cutoff for where you have competent rock masses that do not lend themselves easily to being removed even by physical excavation methods. And that correlates to some degree with the caterpillar analysis relating seismic velocities to the overall rippability of material. In their plot here on the right, highlighted in red, the granitic rock, they're showing it to be more on the order of 6,000 to 7,000 feet per second as being unrippable. But those are good numbers to keep in mind when you start thinking about the relative erodibility of materials, because the rippability parameters go into our rock erosion assessment. All right, so we're looking at the seismic refraction profiles. The upper one is line 1, and you can see down on the map here, it runs across the spillway from upstream to downstream. Line 3 is the lower refraction profile, and it's on the left side of the spillway and also from upstream to downstream. So they follow kind of the same overall trend. And what we see is that at the weir location, which I've noted kind of at around station 300 to 350 on each of these profiles, that the thickness of material that had less than about 5,000 feet per second is quite thin. It's less than 5 feet in the line 1 above, and almost nothing or very, very small in the line on the left side on line 3 below. The interesting thing too is you can go upstream and follow this 5,000 foot per second contour, and as it gets toward the reservoir and toward the natural ground surface and natural topography, you start getting a much thicker section of lower velocity rock. So you have 40 feet or so on the upper profile and maybe 30 or more on the lower profile. But that's as the ground surface is sloping back toward the reservoir, that part of the seismic line is getting more and more coverage in what might have been existing weathering profile or weathering grades that transition. What we see is below that 5,000 on both these locations, we are getting up to almost that 9,000. Between the blue and the red, we're up at almost 9,000 feet per second at less than 15 feet of depth. So it does correlate with the geotechnical logs that show significant improvement in rock mass quality, rock mass strength, and conditions with depth. And keep in mind, at the Spillway Weir, we're at 140, 120 feet below the original ground surface, whereas upstream, we're really near the ground surface, the original ground surface, or at it. All right, so now we move a little bit on the downstream side of the spillway. The upper line, line 7, you can see kind of runs from the spillway down toward the reentrant, the natural reentrant drainage channel. And we have the spillway weir there again, and it confirms the previous recording, previous line number 1 we were just looking at, where we have less than 5 feet of depth before we get into rock that is greater than 5,000 feet per second. So it's pretty the refraction data is showing us pretty confident, pretty resistant rock masses. The lower line, line 6, kind of runs across the spillway but down toward the drainage reentrant channel. And you can also see it's flipped. So downstream is to the right on line number 6 on the refraction line below. And you can see that now we have this line, the contact with 5,000 feet per second is actually getting thicker and thicker. And on the right side, the downstream end, it's up toward 20. So as we get near the existing natural topography, as we're closer to the existing topography before the spillway cut, we're getting closer and closer to the weathering zones that have been in place for tens of thousands of or more years. And when we get into the heart of the cut, deeper part of the spillway, at the spillway weir location, we're having very, very high velocity rock masses show up at the ground surface. All right, so the project developed a scaled physical model of the Tule spillway, and we see in the upper left photo the arched spillway, arched OG spillway with the apron extending downstream, and then the abutment training walls. And because of the arch and the orientation of the structure relative to the approach channel, what seems to happen is that water starts to pour over the OG, but it has a leftward directed flow path. So we're getting higher energy water flowing off the weir, and in the hydraulic jump, it moves over toward the left abutment. So we're getting flow concentrations and higher energy water that comes out and gets pushed onto that left abutment. That was compensated for by extending the apron section much further downstream. But the thing to note, and the thing we want to kind of concentrate on, are the lower right photo, where you see the pink, the dye, and where it's concentrated right in and around and near that left abutment training wall area. Okay, in addition to the physical model, a CFD model was developed for the weir and the channel downstream. And what we see here is that during the PMF event, we're getting velocities about 15 feet per second to 20 feet per second in the invert of the spillway channel. And then as soon as we have the water start downstream, as soon as we get the water getting back into the natural drainage channel and the steeper grades, the velocities increase significantly to 25 to over 30 feet per second downstream. This correlates with what we would kind of imagine we would have there. The spillway invert's fairly flat, and so it's transferring water system along that 1% grade. So 20 feet per second isn't exceptionally huge, but when it gets down to 30 feet per second at that reentrant area where it's concentrating, the hydraulic powers are probably somewhat significant down there, especially because we're looking at more weathered or more, more highly fractured rock down in that reentrant gully. Okay, so I guess it's somewhat clear that that the concern was down at that transition area, where the spillway discharges into the natural gully, the area that had eroded previously in 1966, the area where we're seeing a lot of more highly weathered and more highly fractured granitic rock. It's closer to the original ground surface, so it might be exposed to more of the elements over a longer duration of time. So clearly that was a concern for the design team, and we needed to understand what the rock scour potential is. This is also in light of the fact that Oroville Spillway had failed a couple years previously due to undermining and erosion and exploitation of a highly fractured shear zone or deeply weathered shear zone that transected up and across the spillway foundation. So how do we make sure we don't have that situation? How do we characterize it? So a consultant was brought on board that has significant experience in rock scour analysis, and they performed this scour potential study for the Army Corps. And the sequence of events for this failure mode would be related to one, initiation of the natural channel downstream. So this is in the weathered granitic rock where flows get concentrated, the velocities go up, the stream powers increase, and you have more aerated and agitated water that can exploit that weak material. The next phase of this, though, would be to head cut about 550 feet upstream along a potentially weathered, more weathered feature, geologic discontinuity or geologic weathering zone along the left side of the spillway. We would head cut all the way to the apron. Then we would down cut below the apron sill and maybe below the cutoff or those key walls, those erosion resistant key walls. And so the study that was performed focused on these three phases of rock erosion and head cut: scour progression and down cutting progression. Thing is, what this rock study did not cover, and this is what we have to really think about in the risk assessment, is that it did not do anything with respect to the apron removal, right? So lifting 3 to 6 foot thick anchored slabs off of what might be competent rock. It did not assume any head cutting under the apron or under the weir. It doesn't assume any of the arching structure of the weir, and it doesn't assume any of the 3D structural effects that would provide some resistance to having to remove the weir. So they studied, or they looked at, these first three parts of the failure mode, but they did not, progress the failure mode all the way up. But that's okay. That's what we do with their data. We use their information or information we collect, and then we bring it into the failure mode and make sure we understand which part and how it intervenes or intersects with the failure mode sequence that we develop. So for the head cut initiation, the project is fortunate because in that 1966 flow event, we did experience erosion, and it's erosion that we can measure when we compare the pre-1966 contours against the the current day contours. So you can see how much material was eroded, how the channel changed, how the morphology changed during that event. And so this was used by the consultant to analyze the initiation using shear stress analysis and detachment rate type evaluations. And they were able to come up with a threshold criteria for the material that did erode during 1966 because we knew the stream power and the flows. Okay, so they evaluated all the different rock masses, identified or delineated them based on some of the geomechanical mapping that the Corps did, and from some of the drill holes. So they were able to classify 5 different rock mass types or rock mass zones in the spillway. They identified the left abutment wall, which is moderately weathered. They identified the left floor, the spillway, on the left side, the area where we've had our concerns that there might be weaker rock. So that's moderately weathered to highly weathered, shown in the red belt running from the re-entrant channel back up to the sill. They looked at the right floor, which is not very weathered at all to unweathered, and very strong, very competent, and composed of very resistant granitic materials. And then the right wall, which is slightly weathered, but not nearly to the same degree as any of the others. So they were able to identify the stream power erosion initiation threshold for each of these different rock types. And that's plotted down in the lower right on the Annandale chart, if you'll recognize that. So those can be then correlated to stream powers and flows during the hydrograph, along the hydrograph progression. So the one thing to understand in a risk assessment when you're using this data is that there's a lot of assumptions that are made to derive these criteria. And one of them for this evaluation was that the conditions at the re-entrant channel, the highly weathered granitic rock that's on the left floor, that material extended along the left floor of the invert, of the spillway invert, and it is up to 40 feet wide, which doesn't necessarily fit with field observations or geophysical observations, and that it extends to almost an infinite depth, right? So that is a block of weak rock that extends to the center of the earth. It has no vertical variability or vertical improvement in the rock mass we see there. So a lot of this analysis, a lot of these steps, and a lot of the progression of this is related to a lot of conservative assumptions, and there's some others I'm going to point out as we move through the analysis that was performed. So when performing the risk assessment for a rock erosion type of analysis, we also have to put some time or temporal controls on the progression of the failure. So it's important to understand the outflow, spillway outflow hydrograph, the durations of varying flows and the magnitudes of varying flows, and being able to position your failure mode on the hydrograph throughout time, I think is a critical part of evaluating the progression and the potential and the probability of this event occurring during this PMF or other type spill events. Okay, so based on a really thorough, comprehensive review of the technical and physical assumptions and aspects of the rock scour erosion analysis that was performed, our conclusion was, and we documented this pretty well, was that there are multiple layers of compounding conservative parameters, conservative values, conservative assumptions for both the rock mass, the stream power, and the erosion mechanics that went into evaluating the head cut, or the initiation, head cut, and down cutting parameters that are presented. One of these assumptions was that the peak flow, the peak stream power, the highest stream power possible is applied at initiation, at head cut propagation, and at the scour depth at the end of the apron. And it assumes infinite time. So these assumptions really aren't realistic because it takes some amount of stream power to trigger initiation. Then it takes some amount of stream power and duration for head cut. And then it takes some amount of stream power and duration to get the depth that are necessary to start to undermine a weir or the apron slab. So the problem is, if you have to put this into a temporal aspect, where are you on the hydrograph relative to all these events? It's a difficult thing to do, and you can do it qualitatively in the risk assessment based on some of the information provided in that report. But we have to consider where you are on that hydrograph. If you're on the falling limb, the stream powers are reducing quite rapidly at some point. So you may not have the energy or duration to create the problem. The left spillway channel floor was analyzed in their analysis using the very weak poor rock mass properties, similar to the weathered material that was observed in that reentrant, that natural drainage channel downstream, which was close to the ground surface, close to the stream flows. It was getting wetting and drawing quite frequently. So I would expect a natural surface to have much higher weathered than when you go 120, 140 feet below the natural ground surface in the heart of that right abutment ridge. And that doesn't necessarily correlate very well with our geotechnical data. The weak weathered and highly fractured rock along the left part of the spillway invert was assumed to extend to infinite depth as well. And none of this seems to be supported by the geotechnical data, not by the drilled hole data, not by the field mapping observations, not really by the geophysics either. So we have a break, and these assumptions are maybe a little bit conservative. This is also interesting. The PMF, this was a conclusion of their report, the PMF has a 3 to 6% chance that there will be 60 to 80 hours of flow remaining to scour vertically at the end of the apron. So the initiation has happened, the head cutting has occurred, and it's head cut to the end of the apron. There's only a 3 to 6% chance that we're going to have some amount of flow duration remaining at the end. So basically we have only a short amount of duration left on the falling limb of the hydrograph to not only downcut and undermine the apron, but now we have to also head cut and remove apron slabs and fail the arched spillway weir. So if the initiation at the downstream channel, the reentrant channel downstream, requires PMF stream flows to initiate, this means that the head cutting, undermining, slab, and weir destabilization all have to occur on the falling limb of the outflow hydrograph as the stream powers are decreasing and decreasing and decreasing. The assessment does not include undermining, uplift, and removal of the aprons, or the additional head cutting about 200 feet to get under and destabilize multiple OG monoliths. But that's okay. Their analysis and their scope was not to do the risk assessment. So we use their data, their assumptions, their information, and then we put this into the failure mode sequence, right? So in our overall failure mode sequence, we can account for these factors as well. So overall, their report and their documentation and the technical analysis was extremely useful. It was informative, it was well compiled, and we could glean a lot of information and data from it, and it strongly informed our risk assessment. But it does require really high-end technical review and interpretation and judgment of their conclusions, and communicating that information to the rest of the team so everyone else knows what the assumptions are and what the information is that's contained in that. And then we apply all those results into the design and our risk assessment. Okay, so now let's get to the kind of meat of all this. You've got background on geotech, got background on design, got background on the analyses, the scour analyses, and other information. So we have to put all this together and bring it into the risk assessment. I'm going to jump to the end real quick here. We identified almost 32 potential failure modes for the spillway structure. However, we screened out or combined some of them because they had some similar mechanics down to 7 credible failure modes. And then 2 of them were determined to be risk driving, and both happened to be geotechnical and geologic related. PFM1 was the head cut initiates, is what we just talked about. This was the main concern for the dam, was the head cut initiates downstream at that channel reentrant. It head cuts 500 plus feet upstream, undermines the apron, undermines the spillway weir foundation and multiple monoliths probably, and results in sliding, failure, or breach of the spillway weir. PFM 13 was also identified, which had been somewhat considered in the design with the training walls, but This is one that we ended up kind of focusing on a little bit more. And this would be like slope instability on the downstream left cut slope face and adjacent to the concrete sidewalls, or those wing walls, fails the concrete, crushes the concrete, exposes the foundation rock, which is then scoured because of all the spillway flow is now concentrated, right? If you remember from the physical model, it all gets concentrated right into the left side of the spillway. So then this results in removal of the buttress of the arch or undermining of the monoliths on the left side. Okay, so let's look at a graphical representation or graphical sequencing of these failure modes. So PFM1, right? Here we start. We have a flood event. It's the PMF or something similar to the PMF, where we have enough hydraulic energy and enough erosive capacity to initiate erosion down at the downstream toe. That's on the right side of this image. So the erosion starts and it progresses. It progresses upstream 400, 500, 550 feet upstream along the left side of the spillway invert, where the rock has been identified as being more highly weathered or highly fractured, and it might have lower, erosion resistant capacity. And then we have to downcut. So it's cascading, flows are cascading off of the end of the apron. They're eroding the rock downward below the cutoff key wall, right? So we're undermining and we have to have failure of the key wall. And then we have to undermine, lift, and remove the anchored and reinforced apron slabs. And we have to head cut back upstream under all those features and remove those features another 150 to, or 125 to 150 feet to the undermine the weir, to the toe of the weir. Then we have to undermine the left abutment weir, causing rotation into the scour hole, some sort of destabilization of the arching forces, or sliding or removal or loss of bearing capacity, causing the weir to fail. So at some point we have to lose and breach this structure over on the left side. So that's the failure sequence. That's a graphic that we use in sequence. It's really helpful for everybody to watch these and see these in detail and in all the nuanced components, because this is what we then form our elicitation on. All right, so once everybody knows the failure sequence and knows as much about the conditions and the assumptions that were made in various analyses, the data from the geotechnical information, the interpretations that the geologists, geotechs are making, we sit down and as a group we compile all of the more or less likely factors. These are the factors that either promote the failure to occur or make the failure less likely or more difficult to occur. And you have to be very, very diligent with these. You don't want to repeat them. You don't want them necessarily to conflict with each other. So a lot of thought needs to go into these more or less likely factor tables. But this is probably the best part of the risk assessment, just as a matter of opinion here. The compiling the more or less likely factors, defining them, being very clear about the things that go into our assessment of the probability of this event occurring from initiation to failure is all compiled and summarized in these tables, and it helps inform everybody. It helps with the elicitation of values and that sort of thing. So I just put this up not for anyone to read necessarily, just to see the more or less likely factors that we came up with for the erosion failure mode. Okay, so now we'll look at some figures that we developed, sequential figures to describe the other failure mode that we were pursuing. So the left spillway abutment slope failure that fails the concrete sidewall and exposes it to the high velocity flows, because this theoretically happens earlier in the spillway event. Okay, so let's see if I can go through this. This is a busy slide, so I tried to break it apart into a couple sections to help with some 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 visualization tools and some other things. Okay, first thing we have is all of the identified rock mass, rock joint features. We have up in the upper left area, you see the 1959 rock slab failure, and it failed on an out of slope dipping joint that was identified as the N joint by the design team. Those out of slope dipping joints occur quite frequently in this slope. They seem to be all over the place. They have certain orientation, certain configuration relative to the slope, and they are then controlled by release planes and side planes that allow possibly kinematic removal of blocks of varying sizes. So we see that in the analysis, in the construction photos, and on site in the field mapping. And we can see this here when we plot all that up. I'm not going to go through the details of StereoNet, but these are the N joint and another joint, the side joint, S joint, showing both planar sliding on the N and wedge sliding on the intersection of those two joint angles out of that slope. Okay, so now we can see that the first phase of this this failure mode is that a relatively large rock wedge, something bigger than in 1959, is formed by those out of slope dipping discontinuities, joints N, and there's another one, S, that also comes out of the slope. These fail when high pore pressures in that abutment act at the base of and on the side planes due to increased precipitation. So we have no instrumentation in this left abutment slope. We don't know where groundwater is. We don't know how it has behaved over time. So the assumption is that maybe we get high groundwater from this PMF event. We get a lot of rain on this slope, and it elevates the pore pressures, and it can trigger this type of wedge failure that's shown here by the red faded back area, where we have the release joint in pink, the S, the side joint in yellow, and then that out of slope dipping N joint, and that fails down onto or through or deforms the left concrete side training wall. Okay, the next part of this failure mode is that block then causes this reinforced and anchored left sidewall training wall to be heavily damaged, deformed, crushed, and basically fail into the flows, into the spillway flows, which again, remember, they're concentrated toward that left abutment. So we expose the rock in this immediate area. It's exposed by this failure and exposed by high and attacked by potentially high flows and high velocity water. So the head cutting then exploits the rock right in the abutment, right at where the arch is embedded into the rock mass. And the head cutting then erodes a much shorter distance around that abutment and under the foundation as well. And it causes destabilization on the left side of maybe multiple monoliths over on this left side, and we breach the reservoir. This is also shown in plan view with the StereoNet and kinematics in plan view, the release joint, side joints, and the potential varying out of slope dipping end joints that are there. So this becomes our more concern with respect to failure mode, because the flows are all concentrated here. If we get a failure, then the erosion only has 50, 60 feet of rock to remove in the duration that it is. So we did some kinematic analysis, lots of kinematic analysis, and then some swedge type analysis to look at this. Again, we didn't really know what the pore pressures were, but we had to make some assumptions. Okay, again, just a figure showing all of those more or less likely factors that make this failure mode more likely to occur. All the observations, the stability analysis, the out of slope dipping joints, that sort of thing, the unknown amount of uplift pressure or pore pressure that may be in that slope in that area. And then we have the less likely factors, maybe that our concrete wall does have some anchoring, it has drainage in it. We have the thrust forces of the OG pressing into and onto that slope. And so this is again reiterating the thought and the attention and amount of detail that should go into these more or less likely factors. These really form a lot of the basis for the elicitation, for the team discussions, and for everybody to understand the driving conditions for not just their elicitation assumptions or impression, but the communication between everybody. Okay, so here was our updated risk characterization for PFM1, the head cutting, initiating and migrating upstream and failing the dam, and our elicited estimate of PFM13, the slope instability. So we also, I would like to point out, I didn't really have a slide in this, but we performed the PFM1 elicitation and evaluation. We did it with the key wall, the erosion resistant cutoff wall at the toe of the apron. We did it with that structure in place and without that structure in place. And what we found was that it did not impact the risk in any measurable magnitude. So we ended up pretty much plotting in the same very, very low likelihood of this failure leading to a breach with or without that key wall. So that's an interesting part that came out of this RID evaluation. And then we evaluated the other slope without measure. So on PFM 13, we did not have any left slope or training wall stabilization measures imparted. So we plotted up a little bit higher on the risk characterization matrices. Okay, so then the team sits down and we start thinking about what we can do for PMF 13. What structural measures and what features can be accounted for. And so a lot of that discussion involved maybe thicker training wall, concrete slopes, more drains, and then it really was focused on anchoring the training wall back behind the potential slab failures, the wedge failures, and putting up some slope stabilization structural measures into that design, and also adding drains up into the abutment to maybe get water out of that slope. So when we bring those structural elements into the training wall design, PFM 13 can be significantly reduced by almost order and a half magnitude. Okay, so the major findings from the risk-informed design of the new spillway structure, the team identified concerns that were associated with the left abutment slope, stability, and ability of the abutment to accommodate kind of the hydraulic loading expected from the crest. So recall that all the water from after it flows over the crest gets concentrated onto that left abutment slope. So those two things really were driving some of those concerns, is the concentration of water and the potential for slope instability and maybe damage to the training wall. The rock quality on the left spillway invert might be worse than on the right spillway invert, obviously. I mean, the right side was highly competent, highly resistant. But the conclusion was that during excavation of the apron and the weir structure, we would really be able to characterize, map, delineate, and understand the extent of poor rock in the left abutment. And so that if poor rock is encountered, it should adhere to more appropriate and robust foundation acceptance criteria. So over excavation and backfill grouting or backfill leveling concrete in areas where rock is excavatable, not where we have to blast it out. The spillway weir, abutment monolith, and the thrust block tie-ins are critical to the reliability of the entire structure. We also found that the structural design philosophy, so the arched spillway weir, the whole concept is that it transfers loads outward into the abutment through arch action. So you can undermine, it takes a lot of effort, a lot of work, a lot of undermining volume has to be removed to destabilize the arching effects, or to get the arching effects out. And a structure like this can probably span over somewhat large erosion hole. It may have to involve multiple monoliths for it to slide or or rotate into a large enough erosion hole. It's likely that the installation of a cutoff wall downstream in the spillway will be costly and does not provide a equal increase in the reliability or risk reduction of the structure. So we were able to eliminate the key wall at the heel and at the toe of the apron of the structure, and that was a benefit from the RID discussions and optimization. And if the design recommendations developed during the reevaluation of the PMF are implemented, the RID team judged the risks associated with spillway raise to be tolerable, according to Army Corps codes. Okay, so after all that, now we get to some of the final, the more advanced designs that are counting for some of the RID findings, where now we have the anchored OG weir with a heel shear key. We have only 2.5 foot thick apron, so it's reduced from 5. And we also eliminated some of the over-X or the leveling concrete. We have a 5 foot thick apron key at the end, so as opposed to 30 foot deep columns for erosion protection, it just extends about 5 feet down into the toe, and that's also to accommodate some of the hydraulic considerations, I think, and some of the design criteria that others had in mind. And then we would only over excavate weak or poor quality rock that was that can be observed, mapped, and identified, and can be removed with mechanical methods. And then those zones would be backfilled with leveling concrete. Okay, and then the last part of this is the design adjustment for the PFM 13, the left abutment stability. We were going to flatten and reconfigure the left abutment slope in the vicinity of the OG abutment and the rock wedge and the training wall to provide adequate wedge stability. And this in critical areas. Again, this is going to come down to the field observations, field mappings, and field documentation. This would also include improving the stability using drainage. We're going to put some post-tension anchors through the wedge and into the training wall, so it'll be sort of a anchored block that is got more robust resistance. And then additional excavation on slope to unload the wedge in the upper area. All right, so the conclusions from this presentation. The risk evaluation team looked at the risks specifically associated with design of the new spillway and layout features and relative to the site-specific geologic, geotechnical, and hydrologic analysis and conditions. And we looked at that in a lot of detail. We were able to identify costly design features that did not improve the reliability of the structure or reduce the risks of the project. And that's, for example, the erosion key walls, the head cut key walls at the end of the apron and at the heel of the structure, of the weir structure. We were then also able to identify features that might require more robust design for the conditions and the risk driving failure modes. For example, the left cut stabilization and the out of slope dipping potential wedge failures, and bring some structural elements into the design to help reduce the potential for wall damage during flow events. The process allowed for better understanding of the site conditions and also for optimization of the design for its intended purpose. And we were also able to improve communication between the project team, the district, the division, and the designers, and the risk management center and headquarters. Able to communicate our justifications and basis for design in an efficient and effective way. All right, so all that brings me to the end of this presentation. This is opportunity for any questions, comments, concerns, or complaints. I appreciate your time and attention, and I'm willing to accept or have interactions on this topic or other topics moving forward. Thank you very much.